Hey, hello, and welcome to video number 5 of the Learn Along series. Uh, we are currently watching CS224N Natural Language Processing with Deep Learning. This is a course by Stanford. The professor is Christopher Manning. He's a highly coveted professor in the field of natural language processing. So far, we've had 4 sessions of basically 4 video lectures. I have the links in the description about the original series. These are all just YouTube videos. You can watch my earlier videos to tag along, or you can go to the original series in the description. I also have the lecture course materials, basically lecture slides, some notes, some suggested readings, code and everything. What we will try to do is to go through those for the first 4 videos that we watched. This will also be doing one revision and to a little bit of an additional color to what we had learned about so far. If you're new to this session, welcome. What I'm trying to achieve is to build a sense of community around learning. So happy to be connected with you on social media. My social media links are in the description. Happy to engage in any sort of a conversation around what we are learning, what you think we should be learning. I'm just getting started on trying to hone my skills around NLP, because that's where I see a few of the problems that I want to solve, be it in my current industry I am, or in the potential problems out there that can be solved via NLP that applies across industries. Okay. Hey, what's up, Mayur? We have Mayur Mistry in the chat. Guys, follow him. He's doing great stuff around tech and architecture. He does a whole lot of videos as well. Go follow engineering architecture in the chat. Okay, let's I'll quickly show. Let me switch this to, yep. Okay, so this is the page with all of the course materials. This is also linked in the description of this video. What we'll quickly do is just go through these slides. The objective is not to be to get too deep into the materials or to get too deep into the theory. My idea is to have a good sense of exposure. As long as everything goes over your head, obviously you need to then go back and understand, but the idea is to know what is going on more or less, so that when we get deep into the actual application and coding part of stuff, we have a sense of why it is happening, how it is happening, and at the same time, I mean, even the professor says, like, you don't need to, whenever he covers a whole lot of stuff around theory, and he says you don't really need to learn all of this stuff or remember all of this stuff, because algorithmically a lot of code, like libraries like PyTorch or TensorFlow, already have a lot of these concepts inbuilt. But we'll sort of breeze through these slides. Also, maybe look at the articles attached. Let me know if you want me to zoom in or anything. I think it's set to one slide on screen. I think the beginning part was just around course logistics and just a simple idea of what linguistics is about, what word meanings are all about. I don't see any. Oh yeah, okay. So WordNet was introduced. WordNet basically, as I said, is a thesaurus of all of the set of synonyms, because we need to learn about the context of the word at the same time trying to create uh, the meaning for it. So I don't know, let's say there's a particular word, let's say animal. I don't know the meaning of the word animal. So the idea is to either look at uh, the words around the subject word so as to build the context and know, okay, how closer of this word, or how closer is this word to any other word that we know the meaning of. Hence, I think the concept of WordNet came in of, it's basically a set of all of these words, and then programmatically we've been trying to associate the words with other words to build context. Uh, but yeah, I mean, there are some issues as well. When new meanings of words come around, then you got to keep on updating, or you got to keep on adding more words to build context around the new words, because we all know language is ever evolving, and even if there are some slangs that get converted into uh, the mainstream language, then we have to build meanings and context around that slang as well. Okay. Yeah, one hot vectors. I don't think there's anything super important about this, but yeah, okay. For an example of the context that I was saying, let's say there's the word banking, and banking appears in 3 different statements. We know it's appearing with, let's say, system, regulation, crises, and all of that stuff. So then you are trying to build a context of the word banking around all of these words in the neighborhood. Hence, I think word vector comes into the play. It's basically a representation, as it says, word embedding a word representation based upon all of the similar contexts. For example, in these 3 different situations, there are 3 different, similar, whatever the context is, but around these other words, we try to build word vector for banking in itself. And I think it's just a visualization of how far and near all of these. Yeah, I think it's just a simple visualization of where it appears, and also we'll see clusters around what words. For example, you can see, I don't know if you can, yeah, you can see my mouse pointer. Has, had, and have are pretty close to each other because they are pretty close. You can also see need and help close, even if they don't mean a whole lot of the same stuff, or maybe they do. I mean, need also has multiple meanings or applications of the word, but they are still pretty close to each other. So words who have closer meanings or context, even if the meaning may be different, would appear closer to each other. So that's where word to vec came in, and I know Professor had a little code snippet, and we'll do that just after this to get a sense of how it works. But he also mentioned we are not really going to use word to vec a whole lot while we are building the deep neural nets. But yeah, the idea is to have a large corpus of text and then create a framework to learn around word vectors. So yeah, okay, so this is a good example. Let's say we need to find information or meaning or context around into, and we have a window of +2, -2. So we'll look 2 words to the left, 2 words to the right, try to build the context around the center word, which is into in this case, and then like basically do this bracket thing all across the text you have. For banking, you look at 2 words left, 2 words right, and so on and so forth. We got into a little bit of a math, trying to find the likelihood. So if you don't know what the symbol is, it represents a multiplication from position 1 all the way to the left to position T all the way, or however many words are there, and then M is the size. Basically, in the previous example, M was 2, so you have -2 through 2, and you're multiplying the probabilities of the other words given the center word. Center word is basically what highlighted here in red. And then now we try to simplify this expression. Multiplication is a lot difficult to deal with programmatically, so you can simply take a log and log converts multiplications into summations, and then now we have a little bit of a better mathematical expression to deal with. He also said we also did a -1 by t to normalize, and this just creates our objective function. Objective function is basically what we are trying to either minimize or maximize based upon whatever the context, or it's basically the same deal. At the end of the day, we need to be able to get us closer to our prediction to get a good accuracy. So you need to minimize the loss from the expected or maximize same deal, just a plus or minus, but most likely we minimize for an optimization to achieve either a peak or a trough based upon however you create the expression. Then we got into a little bit of a math to sort of show. I don't know if that math is here in the slides, but okay. The thing to know in this expression at the bottom is basically we're trying to calculate the probability of the other word given the center word. That if I'll go back to if given we know that there is banking in the text, what will be the probability that the word crisis would appear? So once we have an idea of, let's say, these probabilities of the words in and around the neighborhood of the word banking, we are able to understand its context. That's why we are trying to calculate the probability. Skipped. Yeah. Oh, yeah. Similar thing was here in the next slide. So in this case, into. So they are trying to find probability, let's say, for the word problems, given that we have into as the center word. Now, here we are trying to, again, the u vector is multiplied with the v vector. U and v are basically the vectors for actual context word, and then v basically is a variable we are trying to solve for. So it's like v is the center word, which is the given part of the equation, and then u is representing the vector for the context words, the outside context words, which we are running through one by one, given the size of our bracket. Now the idea is to amplify the probability of like a large, simply amplify a large probability, because if you just think about these, the values of the probabilities calculated in this expression would be maybe very close to each other, and there will be no proper differentiation between, if there's a probability of 0.39 and there's another one of 0.43, that actually means the same thing. Like how do you create a little bit of a difference between that this word is contextually related a lot more to the 0.43 than 0.39, and which is where the idea of a softmax function came in. It's basically trying to amplify things that are uh, of large probability, so that we are basically picking the top winners uh, when it comes to probability calculation of the other word with respect to the context word. Yeah, I mean, just a visual representation for the same thing, but to train the model, compute all vector gradients. Yeah, I think we'll get into gradients in a little bit. But yeah, I mean, the concept here is that there are two vectors for every word, because one is the context word and the other one is the center word, and then that creates like a 2 times of the universe of vectors that we have to calculate for. So yeah, I think here we come into a little bit of a derivation for our objective function. The professor was trying to sort of give you a context around what basic differences were. If you are not really concerned about the theory part, you might as well just skip this. It's just to give you a good closure around what is actually going on when we are trying to build our objective function. So I'll also just breeze through the differentiation part. We did that in class. You can go back to lecture 1 in this series, and then you can see how we basically log converts a division into a subtraction, right? So you need to just then go and attack individual expressions, and then how do you convert that into, how do you basically pass the gradient or the d by d whatever into each and every expression, and then you have a final expression which makes sense of what we are trying to do. The idea is to minimize the distance between the actual context word and the expected context word, which is calculated through probabilities of the neighborhood region. So as close as we are, then we are a lot closer to the actual context of the word if we are able to minimize the distance. If we have a large distance, we know that we have to move around and then get to that point. It's a classic optimization issue. And then there was a slight gradient descent and learning rate introduced of how that expression would be programmatically used to get to the point where we want to be. Then there were a few nuances of like a model variants, skip grams and bag of contact words. The lecture skipped I think bag of words, or this is again additional information you may not need this at all. More efficiency methods like negative sampling. Right now, as I said, we've just looked at softmax. Oh yeah, gradient descent is here. Basically, if we are here and we know that the expression of actual context minus the expected context would be a little larger, if we are trying to minimize that initially at this point, we also get the slope. That expression also is, because it's the gradient, we get the slope, that we need to come closer and closer to this minimum point. And here the difference between the two would be, I mean, close to zero, if not exactly zero. And then there's this learning rate, because you don't want to just, if there's a large learning rate, you don't want to run away from the territory. You want to stay closer. If you're too far off and you have a low learning rate, you don't want to crawl step by step and take a whole lot of time when you can achieve the same in a lot lesser. So there will be more stuff around learning rate later on, but the idea is to keep on updating. So this is our objective function, or basically the slope, to keep on updating that based upon the old value, and then there's a learning rate, uh, so that we keep on getting closer and closer to our minimum. Yeah, so stochastic gradient descent, uh, the idea is to not use so I mean because it's a large corpus, you wouldn't be effectively, or I mean, if you want to be more efficient, you wouldn't be using the entire corpus all the time to calculate uh, your objective function and then updating uh, the gradient along with that. You would want to just use a few sample windows and then keep on updating that as well. So that's basically the theory of stochastic gradient descent. I mean, again, it's as you see, it's all, you don't need to uh, do something very special. It's a simple evaluate underscore gradient. That's what it is. You just need to feed to the algorithm what it actually would mean uh, in order to achieve more efficiency. I think that brings us to the end of lecture 1. If you have any questions, if you want me to repeat something, please add that to the chat. Let's see what we have in the notes. I'm guessing it will be more of a, yeah, I see. So yeah, if you want, again, if you're interested in more theoretical understanding of what's going on, happy to either you can just watch the videos, or simply you can go through these. It's all involved. It's all included. Can't speak for some reason. It's all included in the videos description, the course materials, this page basically. Okay, so there is a code, and okay, it will take me to let's see if, come on, you're able to just run the code, or yeah, okay, so there's a notebook in this zip file basically. So what we'll do is just replicate that and try to see what happens. I mean, it's just for our understanding. We know what's going to happen, but at the end of the day, the idea is to get as hands-on learning as we can. Give me 1 second. I'll just quickly set this up so that even for our other codes that they might be in the for future lectures or so on, we'll be able to quickly jump to the code as well, as long as we understand what's going on in there. Okay, I am opening a Google Colab. If you don't know about Google Colab, it's basically a great plug and play. All you don't have to do anything. Everything is pre-installed. I mean, usually we just try to install everything through Anaconda, run Jupyter notebooks on a PC. It's not that effective because, you know, we don't really have that level of computation power in our laptops. I mean, if you have, that's great, but if you don't, you need a good plug and play solution. Google Colab is a great, and I'll show you in just a minute. I just am running a few things to make sure this runs properly, and it is not for some reason. I can just upload this. Yeah. Okay. Sorry about this, guys. Oh yeah, uploaded. Nice. I will open this in Google Chrome. Yeah, there we go. Okay, so there is a Python notebook basically in the course description. So I just ran this into my own Google Drive. You can just add Google Colab notebooks, and then all you need to do is go to runtime and select a GPU. You don't need a TPU. That's a buzzkill, but an overkill. But GPU, save, and connect. Google gives you, I think for 12 hours you can allocate you a good amount of GPU space and also disk space for you to run computations. So if you're just trying to, for practice purposes, you're trying to do something, I think this is a great way to just quickly plug and play and learn. I'll maximize a little bit so it's easier for you to also follow. Okay, so word2vec, basically what we were slightly getting into this past few minutes. GenSim has a library around word2vec, so that's what they're doing. GenSim isn't a deep learning package, it's a package of word and text similarity modeling, which we are also basically trying to do. And you import NumPy, Matplotlib. I'm assuming this is all for getting stuff visualized. Import PCA. I don't know where we'll do PCA, but let's see. If you use Jupyter Notebooks, Google Colab also runs in the same fashion. It's just basically a mirror of how this works. Yeah, one of the things that was mentioned was the glove word vectors. Stanford created their own glove as like the library of words or word vectors, so that it's a little bit more efficient, it's a little bit more accurate. Stanford realized that whatever's out there is too robust and takes more time and gives less accuracy, so they were trying to create something of their own. So you can download the glove vectors from the glove page. They're inside the zip file. I don't know if we can run this because this will really require me to, yeah, okay, I need to download the zip file. Wait, nothing will download it. Here's the sub page. Yeah, never mind. The idea is to basically load the glove database and then find the most similar word to a particular word. And I know the professor was also trying to just see what it shows is basically like a code snippet. I don't know if in the preview code he has the solution as well. Oh yeah, he doesn't. Okay, but the idea is to have the most similar one basically finds all of these words that are coming right close to the subject word. So I think, for example, Obama had Clinton and a few other, obviously Barack, and a few other the US presidents, because obviously presidents' names are coming a whole lot of times together than any other word that you can probably think of. Maybe there would be a few words, like probably the word just president. And similar to banana, there were a few fruits that were named with a very good probability. I think more than 60 or 70% of the probability of their appearance. Maybe even like whenever there is a database of fruits, there's always these words coming together, and maybe that's happening for a whole lot of time. There was this one quick exercise, and I was expecting this to be in the slide. I'm assuming it's in the second slide, because I remember this was briefly discussed in the class. I'll just look for with the fact that there were a lot of things that were skipped in class is, I mean, good and bad. One, the professor knows it's too much for you to really get into and try to understand what's going on, but at the same time it's difficult to follow when you're just skipping through a bunch of slides. But yeah, the idea here was basically, if man is to king, what will be woman is to, and the result. So if man is associated with king, there needs to be, and then you're negating man. It's like obviously a vector way of representation. You're coming back into the man dimension and adding woman. What would be the result in case of king? And the answer was queen, because just like man, king, woman, queen. So you can do similar words, you can do analogies, you can do what doesn't match and stuff like that. PCA wasn't really spoken about, so I'm assuming this is more for plotting, just a visual representation. You can go through this code in your own time, or you need to install these club vectors and everything, but I think as long as you understand the idea what's going on, we should be fine. But I think, yeah, we can get on to lecture number 2. We can look at these suggested readings real quickly. I know these are papers and everything. If we find something interesting, we'll probably look. Yeah, I think we have spoken about all of this in the class as well, a little bit. So yeah, I mean, I'm not reading this paper, but if you want, go ahead. Okay, lecture number 2. Yeah, sorry, a little bit of jumping around, but the idea is to also cover as much as we can, but also not get too deep into the stuff that we don't understand. So it's a good balance here. I'm drinking tea, by the way. So this is where we left, sort of, the center word into, and then there are other words trying to find probability. This is where u and v, okay, I think I didn't explain this while going through the earlier slide, but u is the outside word vector, v is the center word vector. When you do a dot product, you're basically converting that into a column vector, and then softmax doesn't change the shape, but it changes the probabilities that are there inside, so as to show the higher probability ones a lot more than the lower probability ones. And then I think this is the visualization sake. You can see biology, chemistry, and evolution stuff coming together, library, educators, Samsung and Nokia. Sunday, I see Saturday, Tuesday, Christmas. It's basically like days and stuff coming together a lot closer to each other. 3, 7, 8, 2, 0, yeah, all of these numbers. I mean, there's some other words like lilac. There's nothing closer to this one. I mean, obviously it also depends on the number of words that were initially chosen, but we looked at gradient descent a little bit. The idea is to be as efficient as you can. So instead of choosing the entire, you just choose a few sample of windows, uh, and you're also changing the window as and when you are changing the gradient. So it's a little bit more efficient. I mean, I don't know the theory behind how we can be, I mean, intuitively kind of makes sense, but I don't know how to prove it. So I just buy that at face value. Because if you have millions of word vectors, and if it is going to be computationally super extreme to achieve something if you are not being efficient at all. The skip gram model, I think this was slightly introduced because achieving this as a linear function would also be a little bit of an issue, which is where the sigmoid function was introduced as part of our objective function. But yeah, there are more ways to just improve on how do we get stuff just like softmax function. Sorry, increases the probability for the expressions which are already higher so that they are more prominent. Same way, other methodologies, this one uses negative sampling, but I'll not get into details here. There are just more ways to do stuff. I don't think we'll be using this at all. Co-occurrence matrix, yeah, I mean, if there's the corpus is of 3 statements and then you try to build a matrix around, okay, how many times they're appearing with one another. Like you see, I appears alongside enjoy and flying. Enjoy comes, enjoy is next to flying. I is next to like 2 times, so it's like the next word. I mean, you can have different window sizes accordingly, but at least for this matrix, the idea is that if there are 2 words, the vector associated with them should be closer to one another. I don't see anything. I mean, it's just too less of the words are very less for us to pinpoint on an example. Let me just see if there's any. I don't see anything. I mean, deep and NLP have like 1 now. Yeah, so these 2 rows would be closer or looking like just the same if the context around the words or the meaning would be close. I mean, that's basically the idea here. It's a very less amount of words in this corpus, so we can't really make anything out of that right now. Yeah, so dimensionality reduction, okay, we can talk about this a little bit. Now, since there are so many words, the shape of the matrix would be it will be humongous basically. We are trying to reduce the dimensionality so as to be fixated only on the words that make more sense. I mean, picking like the top winners, like why would you want the entire set when a few words or vectors at the top can explain the entire story. So you're just trying to create, there's this concept of singular value decomposition. It's basically you're converting this matrix into a product of 3 matrices and then remove the last few vectors out of this matrix so that you have a smaller matrix which essentially still has more or less the same meaning. So it's, I mean, you can look into SVD. I wouldn't say it's easy, but it's not that difficult to understand why we are doing this particular operation. I mean, you need to convert this into a product of 3 so that you are you can at least enable uh, the objective of removing the last few columns and rows, and similarly, I mean, out of this unit matrix, I think it's just a diagonal matrix. So yeah, classic linear algebra result, but we are basically trying to improve. Now the idea is to improve, because we can do everything, but our bottleneck comes into the picture more around computation time. I mean, I don't want to be just sitting here for 48 hours running a simple piece of code if I can do that in 4 hours, 4 minutes. So the idea is to be as efficient as we can, and there are direct ways around. You don't need to do that by hand, obviously. You can just you can see in the code, you can just decompose or create the SVD just with a couple of lines of code. It's a NumPy function. Okay, hacks to X. Yeah, we'll skip that. Yeah, Glove. As I said, Stanford's homegrown corpus. It's just showing differences. It's fast, efficient, and stuff like that. And here it is. I mean, if we try to see similarities, we know ice is a solid. Ice is not. Okay, the center word is ice. Sorry, and X is the other word. So solid ice, this should have a large probability. Gas and ice would have a small probability. Water and ice would also have a large, and some, if there's any random word, would have a lower probability. And when we try to find this computationally, you see, I mean, this is what the values come around. Not that it's too different, but the fact that we try to find that as a ratio of co-occurrence. So similar to ice, we do that for steam, and then we find the ratio of the two. So you know now that ice is a lot more solid than steam is. So that's why you see a large probability number. And it's the complete opposite in this case, where you know ice is a lot less gas than steam is. So yeah, now both ice and steam are related to water, which is why the values should correspond 1. I mean, obviously there will be differences of how many times it has been used. Ice and water go a lot more along than steam and water, but still it's around 1. And similar to any random word, because both of these numbers would be low, individual probabilities around the other word for the context word. Yeah, it's the same concept of yeah, and just more stuff around glove, corpus. Oh yeah, so here it is. Oh, why didn't I see this? So this was the example: man, woman, king, whatever. So trying to find word analogies. It's basically we are trying to find the distance. So the distance between man and woman, and then you transpose man to king and move along the same distance. The word queen would be the most probable word that would appear in that. I mean, I think it's similar distance calculations or glove visualizations of like distance between brother and sister is kind of like distance between man and woman, nephew and niece, uncle and aunt, and so on and so forth. Because here the distance is basically the change of gender, from male to female, king to queen, emperor to empress, so on and so forth. Oh yeah, okay, so now another visualization for CEOs. I mean, I don't know any of these CEOs, but Caterpillar has Oberhelman. So you'd see the distance. It's more or less an understanding of you're moving from the company name to the person who's leading the company, for example. Superlatives, okay. More visualization, but you see there is, it follows the similar trend, because the distance between the two would be the similar representation all across the board. Yeah, intrinsic word, it just shows glove is more efficient. Correlations, there's no, one word can have a lot of meanings. So I think there's a word pipe that has all of these meanings. So it makes it a little bit of different problem to understand. But we basically then do it's like a weighted sum of all of these individual probabilities to get to that word. Okay, I think this was important to just classify. It's basically classifying a word where it lands. And classification is basically just trying to draw the line. So either it's in side A or side B. It's the same expression, or like the similar expression we were looking at earlier. And then also, you can do a logistic regression softmax classifier in order to embolden the differences between the words, as discussed earlier. This is again a computational idea. You take the log and try to minimize this function now with a negative sign. So the cross entropy is basically, I think the simple way is, if a word appears once, so the probability would be zeros all across and then 1. So this value would be negative log of QC, which is like the expression we are trying to, they've not mentioned why it's, let the true probability distribution be P, computed model probability Q. So it will be whatever the probability is. But let's say it appears multiple times, or if it's not really a word that we understand, so we are trying to create a probabilistic scenario, then it will not be 1, it will be some other values in other places. So you, instead of just one word, which will happen most of the times, just having zeros all across and 1, and then you calculate the probability, you would have a distribution based probability. Same, we create the function, try to minimize this. There's just notations and stuff. You can look at the lecture videos. I would say the idea here is basically try to understand what the issues happen. It's around, softmax function is great, but also it's not like obviously the best one, because it's still a linear, or more or less it's only creating linear decision boundaries, which is why we need more deeper algorithmic ways, such as neural networks. This is exactly what it says. And that's it for at least with this one. But the idea is that we are trying to be as efficient to get started at least with the classifier, and the simple ones are naive Bayes, SVM, softmax, logistic regression. These were the starting of classification or classification algorithms, but obviously these were not the most efficient ones out there. That's why we resort to a lot of more advanced neural net versions of the same, or even completely different ones. But the idea is to know how those work, and you can Google, you'll understand. It's not too difficult to get an idea if you want to. If you don't, it's fine, you're not missing out on a whole lot of stuff. Okay, I think the third lecture was super interesting to get an understanding, or at least the basics around uh, neural networks. But I'll quickly just breeze through these links if you find something interesting. Uh, Not going through the notes. Uh, Paper, more papers. Yeah, not happening. Python session review. Okay. Yeah, we can try to do this. There are slides. Is it just reviewing basic Python? Oh, great. I mean, if you're not uh, adept with Python at all, I think this is great. Just a quick understanding of installing and everything basically. And yeah, NumPy and just the basic tools. Oh yeah, I mean this is fantastic. I didn't even know this existed. But let's move to lecture 3, or let's do one quick break uh, before we move on to lecture 3. I think 3 and 4 are a lot more interesting to look at, just from a neural network perspective, because the professor explains what neural networks are, how they work, uh, and lecture 4 is a little bit more around backpropagation. So let's take a quick break for 2 minutes and then resume from there. Okay, welcome back. Let's get straight into lecture 3 without wasting any time, because I feel this is where the heart of neural network understanding lies. I'll quickly set up. Here we go. Yep. Okay. Yeah, this is all just a course logistic stuff, and we continue basically from the classification understanding. I think the professor had breezed through the last few slides in lecture number 2, so he was just trying to cover just that basic understanding of the loss function. Yeah, neural network classifiers would be better than just the softmax ones. Yep, this is, I think we saw this already. Okay. I mean, you can watch the lecture for a much better explanation than I can do. Sorry about that. But essentially, neural networks are imitating neurons in our system, and the concept was that there are these dendrites, which are basically the receptors, and then the axon is where the information is passed through, and it's here you can see it's like one neuron interacting with these 3 neurons, and it's like a cluster of many neurons interacting with each other, which is what we sort of try to do in imitating in layers, if you have a little bit of an idea of multiple layers. But again, it's the neural network is obviously a lot simplistic representation of what actually happens in our brain, but the idea is pretty much the same. That's why it's artificial intelligence. So the concept of a single neuron is now being represented as like a unit is introduced here. They're trying to say, hey, what if there's a function w transpose x plus b, and it's like a simple logistic regression unit. We have x1, x2, x3, and a bias which is sent with all of the individual weights to the unit, and then the result is a function h of x. It's as a non-linear activation, so it can be whatever you choose. W are the weights, b is the bias, h is the hidden layer, because we have multiple layers, and we have h, let's say, as one hidden layer unit, and x is the inputs, as I said. So yeah, it's a better representation. This is the first layer. This is the first hidden layer, and then you have x as the input, and plus 1 into the bias, and b, that becomes the weight of this particular branch. So a network would be running multiple, let's say, we are assuming logistic regression happening on every unit, so it will be running multiple ones, and it's a combination of all of the inputs to all of the hidden layer units. Just a general sense of understanding, but the idea is to have, I mean, we can have multiple layers, so this becomes super complicated if you're trying to just do that by hand, but the inputs would feed onto individual units. Now those units would feed onto another layer, which is now layer number 3. I mean, computationally you can have many layers, but again becomes a little too computationally heavy, is what I was trying to say, which is why GPUs, TPUs to the rescue. But yeah, I mean, 4 layers. We have a multi-layer network, and that's what kind of happens in our nervous system. But we also need to be efficient around the bottlenecks that we would have. A few things around notation. I think this is important to just get a hang of, because we'll see notation all the time, even if we may not require an understanding of notation that well in the when we're coding, but we may need to understand from just the learning perspective, because this is how it's represented on slides, for example. So as I said, x's are our inputs, this is the bias, we have weights. The weight is like wij, I is the hidden layer unit, j is the input unit. So 1 2 is basically it's going to 1 a1, and it's coming from 2 x2. So that's how weights are named. That's the notation. And then the idea is that we need to implement non-linearities. We can't just have a simple linear expression, because even having multiple layers, it's like a linear expression of linear expressions. It's also a linear expression. So we need to have linear, non-linear classifiers, so that we are able to achieve a lot better result for understanding or for learning, quote unquote. This is just a quick mention of NER. This is one of the topics that I think I've said this in the earlier videos as well, where I want to be able to understand and learn a lot better than, it's just an introduction, but in documents, in abstracts, or whatever text is out there, it's important that the code understands what it is. So for example, here it is able to understand that France is a location, LOC is location, Britain is a location, Fischler is a person, PR is a person, NFU is an organization, this Welsh National Farmers Union is also an organization, Lloyd Jones is a person, so on and so forth. So it's understanding the entity wherever it appears in the text. Tracking mentions of particular entities in documents. You basically know how many times a particular word or an entity, as called here, appears in the entire code. It's just showing the same thing. NER is hard, because if the name is First National Bank, how does the system know that the word first should appear in the name of the bank? In this particular headline, is it just National Bank or is it First National Bank? So it's a little bit of a contextual issue. And then same thing for future school. Is this going to be a school in the future, or is the name of the school future? Things become a little ambiguous, and even a lot more when you have double meanings based upon the context. Charles Schwab is name of a company, and also the person, who's after who the company is named. In this text, Charles Schwab is referring, this is a reference to the person rather than the company, and I assume, the code would more often than not pick this as organization, because that's how Charles Schwab appears in the text out there. Word window classification, I think this was around position, classify a word in the context window of neighboring words. I think we were briefly trying to do that earlier, and apply softmax obviously to embolden the probabilities that should make more sense. Let's say it's a statement, museums in Paris are amazing. So now we know there are 5 words, so we have a 5 times into the normal universe of of the vectors. So same thing as earlier, you might have seen this expression. It's calculating the probability of outside word given the center word. Now again, we're just playing around with the math here, but I think there was okay, this I think is a good one, and I'll jump to my notes real quick just to see what I have here. But now these are the x's, the inputs. The hidden layer expression is z is basically ws plus b, so a is like the first hidden layer expression, and then we are trying to find a score. Now score is a one by one, which is just a number. if you remember earlier, this is going to be a multiple, some n by m, sorry, size of the matrix, and then the expression, the first inner layer would be I think a column matrix. Oh yeah, it's mentioned here. So u is 8 by 2, x is 20 by 1. Okay, yep. So the 4, x1, x2, x3, 1, these are the 4 inputs. They have 5 words, so they're 20s to 1 into 1. W becomes 8 by 20. Why is W 8? Yeah, okay. I think that's a good question to have, but let's come back to that later. Let's just buy this at face value for some reason. I don't know why. I'm not even finding that in my notes. Not sure what I'm missing, but the idea is we are trying to reduce this into one single number score. So we have like a score of this particular window where Paris or museums in Paris are amazing. It's basically the phrase of like a +2 -2 window, and then we're calculating a score. Only if museums is the first factor should it matter that in is the second position. Yeah, I mean, the middle layer learns these non-linear interactions. Yeah, that's the main intuition of why we need multiple layers. So, for example, the first word is museums. We know more often than not the in is as a good vector that should follow the museum vector. So this interaction is learned by that extra layer. Let's do some coding. So yeah, I mean, this is how you sort of create. This is the score that you calculate for the phrase, and this is the score of, let's say, some other phrase, and you do a 1 minus, and you're trying to create the math. You're trying to make the math work, so you have a good expression, or whatever the cost function or objective function, whatever you want to call it, that you have to minimize or maximize. You've seen this before, the stochastic gradient. Oh, that's it. Oh, okay. Yeah, I mean, we'll get into gradients, I think, in the next lecture. But leaving aside, I can't recall why the shape was 8 for this particular expression. But the idea is basically we want to reduce this number to a score. I mean, reduce the entire expression, or the s is particular just a score value, so that we are able to either compare or minimize or whatever we want to do. Let's say for this example, we want score to be a number. This is not differentiable, but it is continuous. You can use SGD. Okay. If this doesn't make a whole lot of sense, it will make some sense in the next lecture. But the idea basically here is to understand what neural network is, why are there multiple layers, why we need to understand why there are multiple layers. I mean, and just around notation, because this notation will follow everywhere. You would, I mean, every slide that you would see. Okay, so we'll quickly just open up all of these links to see if there's anything interesting. We can also get into the code. There's a notebook directly, okay. But if you want more understanding, you have all of the stuff. Oh, this lecture 4. Okay, sorry. oh yeah, if you need a refresher on differential calculus, I would say it's important, so just to get an idea. But I think in the next lecture, the professor also sort of introduces that stuff. Natural language processing from scratch. Okay, I think there's a book or at least 45 pages of text to get an idea of the NLP. These are some lecture notes. Yep, same thing. Gradient. I think we will get into this. Oh, classifier slides. I think we can do this. Yeah, let me. Oh, I need to download this. Sorry. Save link as. Give me 1 second. I'll quickly set this up. I'll open the same in Google Colab. No. Stanford NLP. I don't know why I keep on closing my windows. Oh yeah, here we are. Open in Google Colab. I mean, what I'm trying to do is I'm downloading this and then putting that into my Google Drive, let it sync, and then opening up. That's why it's taking a little bit of time, but yeah, ready to go. So lecture 3, word window classification, PyTorch exploration. Should just install unrecognized runtime. Hey, hold on. Why unrecognized? Yep, works. Okay. Our task at hand is to assign a label of 1 2 words in a sentence that correspond to the location. Oh yeah, okay. So this is the named entity recognition. We're trying to find whatever words are there that are basically locations. So you see we have Paris, Germany, Denmark, all of these places are locations. So this is the training data. So we have, you can see 1 associated with the word for location. For example, Denmark, Copenhagen, both are places you have 1 twice in the last row. So it's a simple training set, and now you have the test. I mean, why did we train the test set as well? We only see spans of length 1. Okay. Shouldn't we just not have test labels? I'm a little confused. I don't know what we are calculating here, but we've asserted all of the training sentence words to labels in range. Yep, maybe it follows below. Let's see. creating updates of batch tensors. Okay, this looks something different. Oh, okay. So let's assume we have the following vocabulary: ID to word. These are all of the IDs. Word to ID. So an instance is, for the first row is we'll always have parity. The word we'll always have parity. Okay, that's the first word. Now we are defining function convert tokens to indices, IDs, and not INDs, but return for T in sentence. Let's see how this works. Okay, 2 1 3 4 5. So 2, I'm saying UNK, this is for double L. 3, yep, 4 5. Okay, got it. Essentially it's basically giving IDs, all of these IDs that we have sort of defined, and wherever it appears, obviously it's a 0 1 2 3 4, so on and so forth, to the particular to every row, for instance. Let's convince ourselves that worked. Yeah, please do. So we did that the other way around now, of finding, give me 2 1 3 4 5. I don't know, apostrophe double L is represented by UNK, I'm assuming, or it's like unknown, I don't know, but the idea is that we always have parentheses working, so we more or less get an idea of, okay, this is working. We're defining the pad. So in the word window classifier, for each word in the sentence, we want to get the plus minus around the word, where whatever 0 n to the letter sentence, in order for such windows to be defined for words at the beginning and the end of sentence, we actually want to insert padding around the sentence before converting to indices. Okay, so padding is basically so if the window size is 2, if you want we as like the center word, because there's nothing else on the left, we have like pads inserted so that the range always works, or we'll always miss like the first 2 and the last 2 words if we don't have a padding. Okay, let's make sure this works with our vocabulary. Yep, I think now it's has inserted 2, as the window size was 2, inserted pads in the beginning and the end of the sentence. When we train our model, we rarely update with respect to single training instance. Yep. Instead, construct a small batches of data, update parameters for each batch. Given some batch size, you want to construct batch tensors for the word index list we've created with our vocabulary. For each list, B list, for each length B list of inputs, we'll have to add window padding, add additional padding for the sentence so that it's the same length. Okay, make sure the labels are in the desired format. At the level of the data set, we want easy shuffling, because shuffling from one training epoch to the next gets rid of the pathological patches. I don't know what this means. Make sure we shuffle inputs and their labels together. PyTorch provides data loader that gives us 4 and 5. Okay, great. So we'll have tells it how to do 1 2 and 3. Okay, so sort size is 5. Long tensor, train label 0, print raw train label instance 1, tensor 0 0 1. That's number 1. Window padding 2 sentences. Okay, let's move on and see what's going on here. All of the 1 hot vectors will have zeros, length 1, unfilled label instance This is for number 2. Additional paddings of each sentence. The first one hot is just 1 L naught. This is in the 255 minus, so it's the opposite. So zeros would have 255, 1 would have 254. Still not sure why you're doing this, but let's see. Data loader and partial my collate data window size word ID for some chunk of sentences and labels. Add window padding, pad for lengths using pad sequence, convert our labels to 1 hots, return padded inputs, 1 hot labels and lengths. Okay. Shuffle true is good practice for train loaders. I think this is the fourth step that was mentioned. So now the inputs, the first two padding, and then whatever the words were. Same here. Dot size is 2 by 8. 1, 2, 3, 8. Similarly, so we have a 4 tensor. Yeah, I think obviously we have to spend a lot more time in understanding why we're doing this. For each element in the batch, for each word in the original sentence and ignoring window padding, we've got the 5 token indices centered at the word, but in practice will be crazy slow. Tensor unfold, okay. Model in full. Softmax window classifier. I think it's doing all of these steps again. Just defining. Oh, there's no return or no output. I'm just running this through to get to the end of what's going on. Okay, here we obviously define the learning rate, number of epochs. It's done, okay. And we have the losses for size. Oh, it's a list. Come on. How do you find the list size? Oh, length. Okay, so we had five. We started with were there 4 statements, 5 statements? I'm just going back to the earlier one. Okay, 1, 2, 3, 4, 5 statements. After padding, reshaping, we have 100 losses. Wait, that's it? Okay, I didn't quite understand, as you obviously would have noticed, but I'll have to spend more time on this one. I mean, I get the context of what we are trying to achieve, but yeah, difficult to follow without having a whole lot of knowledge about how this happens, even if we know what is happening. We'll skip that. I'll see if I get a better explanation, or if you do, let me know. But I'll try to look around, go step by step. I mean, with the interest of time, I didn't want to spend a whole lot of time right now, but we'll do that sometime later. Let's get into lecture 4, because I think this is crucial to understand the concept of backpropagation. I think we already got our head around what we are doing. For NER, instead of just like a score number, we are doing finding what that entity is. Remember, it's called as stochastic gradient descent. It's a brief introduction to gradients, metric calculations. Just remember how Jacobian is calculated. I think we did a couple of calculations by hand in class, also following the chain rule. Yeah, you can breeze through these and also maybe try doing a few by hand. I'll skip to, I'll just walk along and see. Okay, yeah. One of the things, if you're trying to, so S is the final score. If you're trying to calculate ds by dw, and we also try to do ds by db, b is the bias. We see that these two expressions are constant. Yep, here you see. So I think we just named it local error signal, because you don't want to computationally do duplicated, like that's what it says. Let's avoid duplicated computation. So we call it local error signal, and I mean, the del z by del w, del z by del v is what becomes our local input signal in order to calculate the particular gradient. So we just name this delta. It's the local error signal. Another computationally important thing. Now there was this issue around, if you try to do mathematically, there'll be a little bit of a nuance associated with what the shape should look like. Now there is one thing that we want the shape to look like in one way, so that our lives are easier, rather than understanding why we did that. So there's something known as the shape convention, which is the shape of the gradient. Del S by del W is the shape of the parameters. So basically del S by del W will also be n by m, because that's how the inputs are also structured. So it's just, because W is n by m, del S by del W will also be n by m. Now we need to do a little bit of a cheating to get to that point, because if you remember earlier, we saw del S by del W as delta, del Z by del W. We just take the transpose of delta and xt I mean this term basically is x, take the transpose of these two so that our shape convention is followed. It's just a little bit of a nuance. I thought it's just good to know. Delta says it's a local error signal and x is the local input signal. Here it is. Now we want this to be n by m, so we have to make this n into 1 and 1 into m so that this happens. It's just a hacky way of making the dimensions work. There's nothing else. This is a better representation. It's a column row and then it becomes into an n by m matrix, just like we have for w. I think it was now a calculation to prove that all of the, so if you remember, these h is basically, it's like a z equals w x plus b. So any z or any weight, as I was mentioning earlier as well, has this convention of wij. So and I is based on what the hidden layer number unit, and j is based on the input unit. Yeah, sorry for the noise in the background. Chicago says hello. I'll actually mute for a second. Okay, it's gone. So wij only contributes to zi. So if you take the delta of, del z by del w, you would see it is xj. So it's like independent of, you've gotten rid of the I. So it's basically another quick thing to know, that it wouldn't really, it's sort of like an independent expression dependent on where it is coming from, basically the xj. Yeah, that's the issue. We need to just follow shape convention, because if we just try to do the math, it would not come to what we want. So use Jacobian as much as possible, like the normal algebra, and then at the end just do a transpose, no questions asked. Derivative tips, yeah, it's just more stuff around than the theory, but back propagation, okay. Now I think we've jumped on to the most important piece of today's session. I know we're running a lot behind time, but just the understanding that a computation graph is basically a representation of what all computations need to happen and what's the flow of information. So this is a product computation, this is an addition, and there's a function application, there's another product. So that's how, and all of these are inputs. So this is just a representation of what we've been seeing so far. X is an input, W is an input. So you multiply Wx and add b, this is your z. Then you have a function operation, it becomes an h, which is a function of z, and then to get to the score, you need to multiply u, or you transpose, it's a dot product, but you multiply the u to the h that we've had here. I think it will make sense now. Yep. So the inputs are like the source nodes, interior nodes are operations, and edges pass along the result of the operations. This is a computational graph moving in the forward direction, known as forward propagation. For back propagation, we basically pass through gradients. Now I think the simplest trick is, whatever was the result here, you're basically calculating the gradient of that, of the final entity, which is also the s in this case, but here it's you see s in the numerator. So the final entity is the numerator, and the denominator is basically whatever result came out of that edge. So here it's just, we normalize this as 1, del s by del s it's just 1. But if we go back here, we have to calculate del s by del h, which was the local result. Similarly, del s by del z here, del s by del b, so on and so forth. So we are passing the gradient back to where it started. So the node receives an upstream gradient. Upstream is forward, downstream is backward. The downstream is towards the input, upstream is coming from the output. So here del s by del h, because that's the result here. Here del s by del z, because that's the local result here. It's just an understanding. There's going to be a local gradient of the function as well, because the gradient of its output with respect to its input, because that's what this function had been doing, converting z into h. So you have del h by del z, the local gradient. And the most important point to remember here is that the downstream gradient is the product of upstream gradient and the local gradient. So del s by del z equals del s by del h, which is the upstream gradient, multiplied by del h by del z. So wherever you want to calculate this value, you just multiply the first two local and the upstream gradient values. Now, I mean, it's a little bit complicated because we have multiple nodes. We don't have a very simplistic operation like this. When we have a multiplication here, like CR equals wx, we're basically, it doesn't show, but we're doing the same thing around multiplying the upstream with the local gradients with respect to whatever the input was. So del z by del w, del z by del x, and just multiply those. Now there's just an example because more complicated functions, and you do the same thing, calculate local gradients all across based upon whatever the operation is, and then start from the upstream and keep on multiplying to get the local gradients all across the board. Here there was a nuance that phi had two gradients coming from this direction and this direction, so you have to add gradients sum at outward branches. So if you're going back, y in this case is this particular node here, so you just have to add those gradients together. And it's just some intuitions that a plus sign would distribute the upstream gradient to each sum. So okay, yeah, so 2 plus sign will just give 2 distribution here. Max would route, so 3 0, it will max the it'll route the max gradient. Product would switch, so it's a 2 and a 3, and then I mean basically because the product is 6, it switches to a 1. It's just an intuitive way of understanding if you're doing things right. But yeah, I mean obviously we're not calculating this by hand. One of the efficient ways, because we've already calculated a whole lot of stuff, let's say we're trying to calculate del s by del b, we've already passed through these calculations, so you don't need to independently do that again. If you're calculating del s by del w, just basically start from here because it's the same until here, and then just continue from wherever you left. Now obviously this is a more actual, real looking what happens. You have to define the forward operations, and then you come backwards. That's like just an example, x into y, you're defining the forward operation, and then now obviously in order to define the backward operations, you need to keep the values of that are being the values that are appearing in the forward operation in order to be able to achieve, because x and y are constantly also changing, so you need to keep something static so as to be able to calculate while achieving backpropagation. A little bit of differential understanding. I think we've seen this if you've done uh, courses on uh, differentiation, of how to hand calculate. If we, I think the professor uses the analogy of if we wiggle the x by a little bit, plus h and minus h, uh, this is how you can sort of calculate manually. But even if this is good to verify, this is bad computationally because this takes a whole lot of time. So just a note here. And yeah, summary, we've mastered the core technology. I think the main things to remember is downstream gradient is equal to upstream gradient multiplied by local gradient. For forward pass, you have to compute results of operations and save the intermediate values. These intermediate values are important for backward pass when you are applying the chain rule to compute gradients. While on all these details, I think that was another point. All of this is just computed for you in the frameworks that will use PyTorch, TensorFlow, whatever. But just an understanding of what's going on under the hood is useful. And I think he had more lecture notes associated with the same. I will look at suggested readings. I think one of the readings was with Andrew Karpathy, that's what his name was. He's a student of professors. He was a PhD of professors. CNN, I don't know why we're not. Okay, neural networks. Okay, there's a course and which has optimization and more detailed understanding of neural networks. Backpropagation papers, old ones. These are more notes on derivatives if you want to look at derivatives. It's a Medium article by Karpathy, I think professors, PhD student in the past, and trying to elaborate why we need to understand backpropagation in its theory form. But other than that, I think we're more or less done. I know the classifier code requires a little bit more of an understanding, but I think we are good, at least on the front of having a good understanding of what is about to happen when we say regularization and when we say what is backpropagation, what is a forward and a backward pass, and just in general. I think there are more stuff here. One of the differences you'll see, this is winter 2020 website and the videos are winter 2019, so there is a little bit of an offset. I just want to see if it is covered here or not, because there were a few stuff other than this that was covered in class. Quickly try to find. Oh yeah, there is a few stuff here. Okay, let me zoom in so that it's easier to read. I think it is now. Yep. So training with backpropagation is vectorized. We're not going too much into theory, but I think there are few terms or few concepts important. Yeah, tips and tricks. Okay, neural networks, tips and tricks. I think this is what was covered briefly. Gradient check. I think this was one that we just saw. Good to check, not to be used in the code. Regularization. I think the idea was that we also don't want overfitting happening to our code, so we add in this expression which sort of, I shouldn't say prevent overfitting, but it almost tries to prevent uh, overfitting once the machine starts to learn more and more on our test, our training set. Uh, you can Google L2 regularization if you want to learn more in detail, but the idea is to prevent overfitting. So just remember this thing: we need to regularize our code in order to prevent overfitting. Um, there are different ways, but I think L2 regularization is one what's briefly mentioned here. Uh, Dropout wasn't discussed, but I know the concept is basically you don't have to. I think this is a good pictorial representation. You don't have to do all of these operations. You can achieve essentially a whole lot of the stuff by dropping out many operations. So this is another tip to be computationally more efficient. Neuron units. So now there were different types. I think the evolution started with sigmoid function, which is basically a curvature starting from 0 to 1. This is the expression, but obviously it wasn't the best one out there, and no one uses this apart from just theory. The other one was 10H, which is essentially twice as steep as sigmoid and moved between. So you can see the values here are from 0 to 1. 10H is minus 1 to 1. So if you want minus 1 to 1, and more steep as in the values closer or with the lesser error would be more active than the further away values. I mean, that's just the idea. And you can see at twice sigma minus 1. There is hard 10H. It's basically a more of like a linear operator, but it's like a kill switch for the values beyond, let's say, minus 1, delta minus 1 in this situation. Progressively, I mean, 10H was better than sigmoid. Hard 10H was also good, better than 10H. The more, but the most important popular choice is the ReLU function. That's the one you need to know. The rectified linear unit, it's basically 0 all the way through, and then it's basically, I think it's x, yeah, it's 0 for all negative values, and then just like x max of z and 0, yeah, based upon 0. So it does not saturate for larger values. It has been, I mean, people found success with this a whole lot, so now this is sort of like the standard, but people didn't want to just completely shut off all of the values on the negative side, so there's a leaky value. I think it's like 0.01 times x, so it's basically you have a little bit of activation happening for the negative side. I think there was parametric ReLU, which basically has y equals to ax, and then you have a as the parameter that you can put in based upon what you want. But ReLU is the one that you basically need to understand or learn that what we would be doing. Data pre-processing, another, I think, a few stuff around normalization and stuff like that. Parameter initialization, there are different ways. I think one that was just briefly mentioned was Javier initialization. I have to look into Javier initialization as well, but the context was the initial values should not be all 0, because you will then start off at all of these individual variables would be learning at the same starting point, and you'll be too far off from where you need to be. So you need to give a good initialization to be computationally more efficient. And I think the Javier initialization would just give, I think the value is like 2 divided by the size of the previous layer plus the size of the next layer, something like that. I think we can quickly look this up as well, but it's basically trying to initialize the weights. If this doesn't look, I think it's something like this, but I'm not sure if this is. Oh, so it's the variance, or the rather than the. Oh yeah, I see. So you want the distribution to have normal distribution, mean 0, and the variance is 2 upon ni input layers size plus output layers size. I had variance here, so that's why I got a little confused, but that's basically the idea. Not too much around why we use what we use, but I think it's just one of those ways. Something better than nothing, but that something carries importance, so you need to do something as well. Learning strategies, I think we've seen this more often now. The question was around learning rate. You would want your learning rate to also vary. There are cyclical learning rates. There are exponentially dropping learning rates. The idea is you want to move faster if you're further away, but slower if you're not. So there are different methodologies on that. Adaptive optimization, I don't know if this was, oh yeah, there are different optimizers. Again, just the professor said there are many. There's an Adam optimizer that works best, so keep that in mind, that we need to apply this. The fact that there are so many evolving methodologies, you're not forced to learn about all of those. You just need to know that there are a few that work best, and it just improves from an efficiency standpoint your code a whole lot. So important to just keep that in mind that whenever you're applying something. But yeah, I think we've gone on for a while now. We're touching on 2 hours. Productive time. I hope this was helpful. I am new to this as well, so I'm learning as I'm also trying to explain this. But happy to take any suggestions on what I should be doing, what I'm not doing properly. If you want something changed, reach out to me. You can always mention that in the comments below. I will be happy to look into that. Next session would be just continuing with our regular lecture 5. It says it's around linguistic structure dependency parsing, but it can be a little different. You can look up what the exact lecture is for. As I said, the links to the original series, dependency parsing, okay, that's what it is. Okay, the links to the original playlist as well as the course materials are in the description below. My social media links are also there. If you want to reach out to me, I have the links to all of the social media, so wherever and however you want to reach out to me, I'm happy to engage with you. You can, the objective is just try, tag along with me. I'll keep you disciplined in learning, because that's what I was lacking myself. I've been just postponing this for ages, but happy to be your accountability partner when it comes to learning. This is the first of many series that I'll be conducting. I am trying to get a hold on the list of things that I want to achieve. So we'll start with one and go on achieving more and more. But feel free to reach out. As I said, links in the description. Subscribe to my channel, hit the bell icon, because I'm trying to be very consistent in my uh, in my timing, because that's what creates a good disciplined mindset. But if you want me to move around, obviously I also try to look at as my convenience perspective of how I can make this as easy for me so that I can continue doing this for a longer stretch than just a burst of few days which usually happens. But yeah, happy to be connected with you. Anything else, any questions, any concerns, I am here for you. If you want me to do another of such review sessions with obviously a much better understanding, we'll do that. We can also bring some other people uh, into this who are better explainers than obviously I am. But with that, I think we are done for the day. I'll see you in the next one.